All right, we're going to be looking at two cases of what's called special right triangles. So again, these are 90-degree angles on these triangles, and they're for two specific cases. One, when you have a 30, 60, 90 triangle, which is one where you have a 30-degree angle, a 60-degree angle, and a 90-degree angle. So that adds up to 180. The other case is when you have an isosceles triangle, which is 45 degrees, and 90 degrees, which again adds up to 180. But again, two special types of triangles that come up. Why are they special? Well, they have these certain relationships. We know right off the bat, 90-degree triangle, I can use trig, I can use Pythagorean theorem, and then we've looked at, say, the law of sines when you don't have a 90-degree angle. But this is, again, a special case for when you have a 90-degree angle, when you have these measurements, we know something about the sides and their relationship. And what it basically says is that if you have a 30, 60, 90 degree triangle, if you know, or actually if you know any of the sides, we'll see, but let's say that you know the height of the smallest side, then whatever this number x is, the hypotenuse will be 2 times as big, and the other base, the longer base, will be whatever that is times the square root of 3. On the flip side, for a 45-degree isosceles triangle, so 45, 45, 90, 40, that special case, if you know one of the sides, you know the other side, but then the hypotenuse will be whatever one of these sides is times the square root of it 2. And so just kind of see where these things come from. If you think about, let's say, if I know an isosceles triangle right here, and I know this side is x and this side is x, I know that if I'm coming up with this side, and I'll call it C, because usually we label the hypotenuse as C, that I could think about it as the two legs squared equal to the hypotenuse squared. This is your Pythagorean theorem. The two sides squared equals the longest side squared. Well, x squared and x squared, that's the same object, so really that's the same thing as saying you have 2x squared. And if I want to solve for the side, to get rid of a square, I need to take a square root on both sides. So if I take the square root, take the square root, that cancels, leaving me with just c. And I have the square root of 2x squared. So there's a couple things to kind of remember here. But one is you can kind of simplify this as, or break it apart as the square root of 2 and the square root of x squared. And the square and square root cancel, so this is really the same thing as square root of 2 times x is the longest side. So like if I knew that this side was 5, then this side must be 5, and then this side would be 5 times the square root of 2. And so they always have this special relationship where it's like saying, okay, if I know this side, I know this side, and then I automatically know that this side will be whatever that is times the square root of 2. On the flip side, let's say I knew that, so that's how we know the relationship is true. On the flip side, let's say I knew that this was a 45 degree triangle. So 45, 45, and 90. And let's say that I knew that this length was 6. So I know the sides, they follow this order, x, x, and then x square root 2. So this is what the longest side is equal to, x times whatever the square root of 2. Then I know if the longest side was 6, I could then say solve for x. And so this would be the case of opposite multiplying by square root of 2 to divide by square root of 2. These cancel. And so while this isn't in simplified form yet, I basically know, okay, x equals this, so this is what that length of these two sides must be. They must be whatever 6 divided by square root of 2 is, that would be the lengths of these two sides. So I can go backwards and forwards, essentially. I can figure out any of the sides of the triangle if I know one of the other ones. So that's if you have the 45, 45, 90. If I think about this triangle, and I know again, how does this sort of work out, the x and the x times square root of 3 and the 2x? Well, let's say again, if I have Pythagorean theorem, and I just said, let this one be a side. if I have x squared, then x times the square root of 3 squared, does that equal to 2x squared? And if I square these things out, I'm going to get x squared, just this first one, that stays put. This whole thing squared, that would be x squared, and then the square root of 3 squared, so that's going to be that. This side squared plus that side squared equals that thing squared. So this would be, first one is x squared. This is going to be x squared times 3. So again, squared gets rid of the square root, and then you square both things. So this is like 3x squared equals 2x times 2x is essentially 4x squared. And then 1x squared and 3x squared is also 4x squared. So this meets our kind of definition of this side squared plus this side squared equals that side squared. And so they have this special ratio, again, that if you know one of the sides, you can figure out one of the other ones. So just to give you a quick example, let's say I know that the smallest side is 1. And I know I have a 30, 60, 90 triangle. Then the ratio is always going to go, and if I go in order of like smallest to biggest, it always goes x, then x times the square root of 3, and then 2x. So if x is 1, that means that I can replace the x here with 1. So the next biggest side would be 1 times the square root of 3, or just square root of 3. That would be this side. And then the hypotenuse, the biggest side, would be 2 times 1, or 2. And so I can get those side lengths by knowing this special relationship. Now, these formulas will actually be on the air test. They give you these formulas, so you don't have to memorize them, but it is useful if you know how to use them. And if you do have them memorized, then it'll just be kind of make things a lot quicker when you're working problems. So we're going to look at a few problems from the notes, and then you guys will have a classwork to do as well. So the first thing we want to look at is how do you simplify radicals so we don't leave square roots in the bottom. So we have something called rationalizing the denominator. All that means is that whatever is on the bottom here, you're going to multiply it by it. So if I've got square root of 3 on the bottom, I want to get rid of that square on the bottom, so I'm going to multiply by square root of 3, because if I remember what that looks like, that would be square root of 3 times square root of 3, which is the same thing as putting it underneath 1 square root, which is the square root of 9, which is 3, and the square root goes away. You can also think about it as this is the same thing as saying you've got square root of 3 squared. The square and square root cancel. So I'm multiplying by 1 in a smart way. Anything over itself is 1. And I'm going to multiply by something that's going to get rid of that square root. So when I want to simplify these things, when I'm looking for the answers, they're going to be simplified in that there won't be any square roots on the bottom. So this is always square root of 3 times square root of 3. So that would be square root of 3 squared, so it just goes away. So this becomes 2 square root of 3, 2 times square root of 3, and then over 3, because these square roots cancel out. Okay, I can't reduce that anymore, so this would be my final answer, my quote-unquote simplified answer. And then number 2, square root of 15 over square root of 6. This one's a little bit more difficult, but again, I want to get rid of that squared on the denominator, so I'm going to multiply both sides by square root of 6. Square roots can combine together, so that would be the square root of, say, 15 times 6, which is square root of 90, over, again, if I combine these, that would be square root of 36, which I know will cancel. Square root of 36 is 6. So again, those square roots kind of cancel each other out. 15 times 6, you could put it together, but if you remember how we like to do things, we look for groups. Because it's a square root, I'm going to look for groups of 2. For each pair, 1 goes to the outside, and the leftovers stay on the inside. So this thing square root of 15 times 6, which is really square root of 90, let's say, that would be the same thing as 3 square root of 10. So the pair of 3's comes out to the outside. 5 times 2 is 10. And then this can further reduce. 3/6 reduces to 1/2. So your final answer would be square root of 10 over 2 for that one. We'll need this sort of trick to make sure we kind of, like when we're checking our answers, that we get the proper simplified answer. So let's look at a couple problems. You see in number 3 that they gave me the 30 degree, and I'll try to keep this up to the side here. They gave me the 90 and 60, so I automatically know that this must be a 30 degree angle. And the way the ratios work is that it goes, the smallest side is x, then the next biggest size is x times the square root of 3, the other base, and then the hypotenuse, so the longest side is going to be 2 times whatever x is. In this case, I was given the smallest side, so I know that x is 5. So if x is 5, that tells me that I can replace it here. The next biggest side is 5 times the square root of 3. And 2 times 5, 2x, 2 times 5 would be 10. So this hypotenuse is 10. And this side right here would be 5 times the square root of 3. And you can leave it like that. Number 4, again, I've got a 30, 60, 90 triangle. So I know the sides are in this particular ratio of x times the square root of 3, and 2x. So let's see which side they gave me. They didn't give me the smallest. They gave me, let's say, like the medium one. So or the middle. So that middle, x, which I know is in the ratio of x times square root of 3, it's equal to 3. So this thing, x times square root of 3, is equal to 3. So if I solve this for x, so if I have this thing, x times the square root of 3 equals 3, and I solve for x, opposite of multiplying by square root of 3 is to divide, and I get this statement, x equals 3 over the square root of 3. So I know that means that x's, this smallest side, is 3 over the square root of 3. And the hypotenuse is going to be 2 times whatever x is, so that's going to be 2 times this thing. So 2 times 3 over square root of 3, which would be 6 over square root 3. Now these aren't quite simplified yet, so I can't leave a square root in the denominator, so I'm going to have to do a little work here. So 3 over square root of 3, if I multiply by square root of 3 on both sides, top and bottom, this becomes 3 square root of 3 on the top, 3 times square root of 3, and then square root of 3 times square root of 3 becomes 3. So this cancels out, and this is actually the same thing. 3 divided by square root of 3 is the same thing as just square root of 3. And to kind of prove that, let's look on the calculator. So I'm going to do square root of 3, which gets me this number, 1.7320, blah, 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 blah. And then is that the same thing as 3 divided by the square root of 3? And it is. You can see that I get 3 divided by the square root of 3. They are equal to the exact same thing. So I have simplified that as much as possible. So there's a couple things you could actually do with that. One, if you kind of go back to here, you can realize, oh, that's just going to be 2 times the square root of 3 now, because that's what this thing was equal to. Or if you have 6 over square root of 3, you can just do the same thing. Get rid of that square in the denominator. This is 6 square root of 3 over 3, and then 6 divided by 3 is 2. Okay, so this longest side, the hypotenuse, 6 over square root of 3, that ended up being 2 square root of 3 when you reduce it. And the smallest side is actually square root of 3. number 5, again, I've got a 60 and 90 degree angle, so this is a 30, 60, 90 triangle. So I know the sides are going to be in this ratio, x times square root of 3, and 2x. This is the hypotenuse, so they gave me the hypotenuse, which is the longest side, so that must have been 6. And if I solve for x would be 3. So the shortest side is 3, and then the middle side, or the medium size, or the longer base is 3 times the square root of 3. And because I don't have any radicals or square roots in the denominator, I am good to go there. So the shortest side was 3. The next biggest side is 3 square root 3, and the hypotenuse was given as 6. On this one, again, I got a 30 and a 90, so this must be still a 30, 60, 90 triangle. I'm going to set up my ratios, the smallest, the next biggest, and then biggest. And I was given the smallest side as 1. So that means that the next biggest size, if x is 1, this is 1 times square root of 3, or just square root of 3. And then 2 times 1 is 2. So the biggest side, the hypotenuse, is 2. And the next side is square root of 3. A couple more. So I'm going to go ahead and label it x squared of 3, 2x. I do have a 30, 60, 90. They gave me the middle. So I've got x times square root of 3, and 2x. They gave me the middle base. So I know that x times the square root of 3 is equal to 5. So if I solve this thing out now, so solve for that middle, solve for that x, divide both sides by square root of 3, I get x equals 5 over square root of 3. And if I go ahead and rationalize that, that means that this is going to be 5 square root of 3 over 3. So that's what x is equal to. And then the hypotenuse is 2 times x, so 2 times 5 square root of 3 over 3. So 2 times 5 gets you 10. So this is 10 square root of 3 over 3. And you can leave it like this. This is as simplified as possible. So the hypotenuse was 10 square root of 3 over 3. And the smallest base was 5 square root of 3 over 3. And then last one for the 30, 60, 90s, you have the hypotenuse. So this is one of our hypotenuse ones. So it goes x squared root of 3, 2x. You know the hypotenuse is 10, so this thing must have been 10. So originally, the number that kind of got you there, if you divide both sides by 2, x is 5. So that's the smallest side. And then the middle one is 5 square root of 3. So the smallest is 5, that's y, and then 5 square root 3. So those are all the 30, 60, 90 ones. Now, if you're looking at it's the same sort of setup when you're doing the 45 degree one. So because you already have a 45, this must also be the 45. But instead of doing x times the square root of 3, and 2x, I'm going to go ahead and set it up as just x, and then x times the square root of 2. So for number 9 here, I know my ratio goes x times the square root of 2. So you're either going to be given one of the bases, which they are the same, or you're going to give the hypotenuse. So I was given one of the bases. So if this one is 3 times the square root of 5, then the other one must be 3 times the square root of 5. So this thing is 3 square root of 5. And then the hypotenuse is whatever this x is times the square root of 2. So this was going to become 3 square root of 5 times the square root of 2. This part was your x, and that square root of 2 is your square root of 2. You can combine these into 1, so that's going to become 3, and then 5 times 2 is 10. That's all for that one. This one again, I know I have a 45, 45, 90 triangle, so the ratio goes x times the square root of 2. So I was given the hypotenuse. This time I know the hypotenuse is 5. So to solve for x, I'm going to divide both sides by square root of 2. That's what x must be, so I'm going to go ahead and rationalize it. Multiply both sides by square root of 2. And you get 5 square root of 2 over 2, which is what x is. So that's these two sides. So 5 square root of 2 over 2 and 5 square root of 2 over 2. And the last couple, again, 45, 45, 90 degree triangle. So you got x times the square root of 2. You were given one of the bases, so you know if that one is 5, the other one must be 5, and then this one must be 5 times the square root of 2. Pretty simple. And then again, if you're given in this last one, x times the square root of 2, you know that this longest side is 5 square root of 2. So to solve for x, I'm going to divide both sides to isolate it. That cancels, and so x must just be equal to 5. So this is 5 and 5. And that is how you use the special right triangles. Again, these formulas, these ratios are on the test, the formula sheet that you're given, that reference sheet. Your reference sheet looks like this. So they give you some conversions, and then they give you some trig formulas, and then on this other sheet they give you some formulas like areas or volumes of various things. They have a probability rule, your quadratic formula, and a distance formula. It's actually from the Pythagorean theorem. Right, and that is